Clouds. They seem so simple. When they appear darker, we pack an umbrella. When they're nowhere in sight, we pack extra sunscreen. Either way, we look to clouds for more information than you might realize. But for all that they can tell us, they actually remain quite mysterious, especially when it comes to how they impact the climate. The question is, because clouds are produced by the climate, how will a changing climate impact clouds? And conversely, clouds have an impact on our climate. So how will changing clouds affect a changing climate? Welcome to Clouds 101. Like all good mysteries, this one begins with a sophisticated scientific concept: Earth's radiation budget. Earth's radiation budget describes the delicate balance between the sun's radiant energy that reaches Earth and the radiant energy that flows from Earth back out to space. About 30% of the sun's incoming energy, essentially the light and heat we're familiar with, is reflected back to space by gaseous molecules in the atmosphere, tiny particles called aerosols, land, snow and ice surfaces, and by clouds. The remaining energy from the sun, roughly 70%, is absorbed by the planet. Most of this absorbed energy heats up Earth's surface, while the rest is absorbed in the atmosphere by gas molecules, clouds, and aerosols. So heat can be both absorbed and reflected by clouds. We'll come back to this later. Heat is also separately emitted by Earth into space in the form of thermal infrared radiation, which is the kind of heat humans can only see through night vision goggles. For Earth's temperature to remain constant, the absorbed solar radiation and outgoing thermal infrared radiation must balance one another. If the Earth system is changed either through natural phenomena like volcanic activity or through unnatural phenomena like humans burning fossil fuels, an imbalance in Earth's radiation budget occurs, and as a result, the Earth's temperature eventually increases or decreases to restore an energy balance. In recent decades, satellite and surface measurements clearly show an energy imbalance taking place that's been increasing. Over the past 150 years, the large rise in carbon dioxide emissions, which accumulate in the atmosphere, has created an enhanced greenhouse effect. This means that energy from the sun still easily reaches Earth, but Earth's thermal infrared radiation has a harder time getting out into space. This has caused a decrease in how much heat Earth sheds. Consequently, we have observed a rise in Earth's global mean surface temperature, an increased melting of snow and sea ice, sea level rise, and more extreme weather events. So that brings us back to the mystery of clouds' long-term effects on climate. Here's what we know so far. Clouds impact the radiation budget in two ways: by reflecting solar radiation back to space, which leads to a cooling effect on the climate, and by absorbing heat emitted from below the clouds that would have otherwise escaped to space if the clouds weren't present, leading to a warming effect. Which of these effects dominates in any given location depends upon the cloud type. High-altitude clouds are typically thinner and colder than low clouds, allowing for more solar radiation to pass through them and reach Earth's surface. And because they're cooler, they emit less thermal infrared radiation to space, so they have a net warming effect on the climate. Clouds at low altitudes, on the other hand, are generally thicker and reflect more solar radiation back out to space. They're also typically warmer, so they emit more thermal infrared radiation and therefore have a net cooling effect on the climate. We also know that when the climate warms, Earth can respond in ways that leads to further warming. For example, as temperatures increase, we see snowpack and sea ice melting away in polar regions, a loss of white surfaces that reflect the solar radiation. That means darker colored land and oceans left behind absorb more solar radiation, and so more heat is added to the climate system. This cycle of more heat, more melt, and more absorption of solar radiation is called a feedback cycle. And it doesn't end there. A feedback cycle also happens with clouds. Climate models predict a decrease in low-altitude cloud coverage over the globe as the climate warms. Since low clouds are the highly reflective type, a decrease in low cloud coverage means more heat will be added to the Earth's system, leading to further warming. And clouds impact the climate in another way too. through the water cycle, producing rain and snowfall. Water at Earth's surface evaporates, providing the atmosphere with a supply of water vapor. Depending on the air temperature and atmospheric pressure, the air can only hold so much water vapor until it becomes saturated. When that air saturated with water vapor cools, the water vapor turns back into liquid water droplets and forms clouds. When these droplets or ice crystals accumulate, that is what we call a cloud. When the droplets or ice crystals within the cloud grow to be large enough, they eventually fall to the ground or ocean as rain, snow, or hail. This brings us back to the mystery at hand. Because clouds both reflect and absorb energy from the sun, impacting both ends of the radiation balance, and play a massive role in the water cycle, any changes in clouds will result in a change in our climate. But clouds are also produced by our climate, so any change in climate will result in a change in clouds. As you probably now realize, the relationship between clouds and the climate is incredibly complex, and NASA is on a mission to understand it. Using NASA's Earth-observing fleet of satellites like Calypso and instruments like Ceres and MODIS, scientists have been collecting vital data on clouds to be able to precisely model their behavior. A key ingredient to unraveling the mystery of clouds lies in the collection of global, accurate, multi-decadal climate data records of cloud properties and their influence on Earth's radiation budget. Once we can accurately and fully understand the physics of clouds through observations, that data can then be used to help improve climate and weather models, so we can better prepare for the future.